Hello, and welcome to the first lecture on the semantics of programming languages. And so, you know, before we can talk about the semantics of programming languages, we need to think a little bit about what programming languages are and what it could mean to give them any kind of semantics. And so, if you think about it, programming languages are an important part, are something you need in order to do programming at all. And programming is part of computer science. And if we call it computer science, well, that's as much aspirational as anything else, because there's a lot of things that go into making a computer work. So, literally millions of people have spent close to a century of effort getting the devices that we use every day working. So, it's not just this mathematical discipline where we type things in and then the magic machine makes everything work. There's a lot of science that goes into it, everything from physics and chemistry all the way up to economics and social science. And so this craft of programming that we do is a mathematical discipline where we prove things about programs. It's an engineering discipline where we're trying to solve a problem, and there's always trade-offs. The traditional engineer saying is you can choose fast, good, or cheap. You can pick any two of these. And so managing these trade-offs in order to make things work is an important part of programming. And as you program, you learn how to do things that how to design a program well so that it's easy to modify. And this isn't mathematics. It's something that isn't quite formal. It's a craft aspect. And even beyond the craft aspects, there's an artistic aspect to it. Many of us here have an aesthetic response to programming. We can read a piece of code and say, oh, that's very elegant, that's very pretty, that makes me happy. And other pieces of code that when you go into it, you feel like, why is a human life being wasted on this? And then finally, the last, but unfortunately not least, there's a degree of bawdry that goes into writing programs and building computer systems. In the real world, most things don't work most of the time, and getting anything at all to work requires a lot of effort, a lot of creativity, and when it comes down to the wire, it takes a willingness to do whatever hacks it takes to get things over the finish line. And this final thing is essential, but it has consequences, and not just in computers, but in all of science and all of engineering, and it has for a very long time. So this right here is a picture from 1879. It is it was a bridge in Scotland, and it used to be the Tay Bridge, and this was one of the first mathematically designed bridges in the world. As you can see, it was not an entirely successful experiment. So the mathematical modeling that people did of how much support was needed failed to take into account the effect of the water flow eroding the base of the supports, and then an unfortunate train disaster happened and many people lost their lives. And it was experiences like this that led to many engineering standards in railway design, both here and in Europe and in America. But it's not just bridges that happen with the railway network. There's trains that run on them, and so this was a fragment of a train that was supposed to run in San Antonio in 1912. So about 30 years after the Tay Bridge disaster, and this inexplicable hunk of metal is probably part of a train. So what happened was there was a massive boiler explosion in the San Antonio Roundhouse, and this is one of the only bits of the train that survived, and the exact causes of the explosion are not especially well understood because the detonation blew up most of the evidence. So this act of Bajri is an elemental force, and one important thing here is that I said it was a boiler explosion. So how do we know that if all the evidence was exploded? And the answer is that there's a train that failed its that we have the records for, that it failed its inspection, but the company that ran the train lines wanted to hit their on time targets, and so they okayed the train to keep running. And so it's largely believed that that's the train that exploded. Okay. So engineering is a mature discipline, right? This is much later, about 100 years later. I guess it's only about 80 years later, 85 years later. This explosion is not a bonfire night firework display. It is an Ariane rocket that is exploding and taking $100 million, or I suppose €100 million satellite with it. And the problem here was not a physics problem like a boiler explosion. The problem was that the Ariane 4 rocket had a very, very carefully controlled self-destruct sequence in order to ensure the rocket wasn't going off course. And if you think about it, a rocket is basically a 10-story building that's filled with high explosives in order to get you into space. And so, the self-destruct mechanism is extremely important in order to keep a off-course rocket from delivering a 10-story building full of explosives to where it should not go. And what happened was that the Ariane 4 rocket guidance control software was so well engineered and so well behaved that the designers of the Ariane rocket decided that they were not going to mess with something that worked, and they reused it in the Ariane 5 rocket. And what happened was that the Ariane 5 rocket was a substantially more powerful rocket than the Ariane 4, and as a result, the numbers that the piece of software kept track of could grow faster than they could with the Ariane 4, and a counter that was proved never to overflow with the Ariane 4 rocket actually did overflow with the Ariane 5. So a number went negative when it wasn't supposed to. The self-destruct system detected this and said, "Uh-oh, we are now pointing in entirely the wrong direction," and then it exploded. And that was the end of the rocket. Okay, so this rocket explosion is the first one that you can really say, okay, it's software's fault. And these kinds of overflow counters, we see some disasters and we should do better than that, right? Well, this logo is a logo for the Heartbleed bug. And as you can guess, a bug that is severe enough that graphic designers are called in order to design a logo just for that bug has to be pretty severe. And in this case, what happened was that the SSL or TLS layer in your web browser is the thing that does the secure connections. So it encrypts your connection so that you can safely send your your credit card details to Amazon or something, and no one can snoop in on it. And it turned out about 5 years ago now that there was a parsing error, an error in the parsing routines of the TLS implementation OpenSSL, which was the most widely used SSL implementation. And because the bounds on an array were not checked, it was possible to craft inputs that would overrun the array right into program memory that they weren't supposed to, and entirely bypass the encryption that OpenSSL was supposed to enforce. And so it turns out that for some worryingly long period of time, basically no secure connection on the internet actually was secure. And so this was a dramatic enough bug that an entire website, domain name, graphic designers, they were all invoked in order to advertise this bug. And let's just say it was a pretty bad bug. And it was an overflow error, just like with the Ariane 5 disaster. Well, it was a bounds error. And so, somehow we haven't cleaned up our act. And we can ask, okay, what's going on here? We had these programming languages to write rockets and to do secure communications, and somehow at a most basic level they failed us. Like arithmetic failed, array accesses failed. These are the fundamental primitives that every programmer relies on, and these primitives are unreliable and flaky. So what's going on? In order to do better, we have to have a better understanding of what programming languages can do and what they can offer us. And so the thing is that a lot of the problems with these kinds of programs is that something happens which comes as a surprise. So as programmers, we have an informal expectation that the operations in the programming language, their behavior will sort of match our informal expectations. And so the question you might ask is, how can we make those informal expectations about what the programming language does precise, and how can we establish that our expectations are actually reasonable? And so this is like the motivating thing for semantics. So, what is semantics? And fundamentally, it's a methodology for describing what a programming language is. And for a programming language, obviously there's the thing we type into the text buffer of our, Emacs or VS Code or Vim or whatever it is kids these days use. I myself use Emacs, which stands for the Editor for Middle-Aged Computer Scientists. And, we type something into a text buffer and we have a syntax, and, with a reasonably well-designed language, it'll have like a well-specified grammar, and you can tell whether something is a program or not. But then there's a more important thing, which is, what does the program actually do? And specifying what a program actually does, like how it evaluates, what values it computes, what side effects it has on the world, like what does the program mean? That is fundamentally what semantics is. And so the question you can ask is, okay, well, how can we describe what a program does? And so I said, okay, well, we have some informal expectations. Where do these expectations come from? And one very obvious answer is, well, the language is defined by whatever the implementation does. So if you have a compiler, you run the compiler on a program, and whatever the compiler takes is what the language is, and whatever code comes out is the behavior of the programming language. And this is not an uncommon practice. There are many languages which are largely defined by their implementation. So you have an implementation, you run it, and that's what the language is. Like, a language like Python or Ruby or Perl, they're often defined in this way. You have a canonical implementation, and the behavior of the implementation, say CPython, is taken as the specification of the programming language. And then, this thing usually works okay until someone finds a bug in the compiler. So you can say that the compiler is the specification, but if the compiler does something really weird, and all the developers say, yeah, that's a bug, then they need some way of describing what the language is supposed to do. And so if you look at something like the C language standard or something like this, what you'll see is a natural language definition. There will be hundreds of pages of like lawyer-like prose saying that in such and such a case, the program is supposed to do this, it's not supposed to do that, and in other cases, what happens is up to the implementer. And so one common source of these natural language definitions is you have a language, and then people say, well, we want another implementation, maybe for another operating system, another hardware architecture, or maybe the core developers just come to hate each other and they decide to go their separate ways, and they both want to have an implementation. And so so to agree on what the language does, they give a natural language definition. And because you need to specify in great detail what the language does, you write a lot of prose that's very lawyerly and very hard to understand. And there's also one more problem, which is that understanding what these natural language definitions actually mean, that can be extremely difficult. There's a reason that people who know a language spec are called language lawyers. And so finally, what sometimes happens is that these natural language definitions, they clarify many things, but actually getting down to the point where every last detail is specified in an unambiguous way, that drives people to mathematics. And so what the people start looking for are mathematical specifications of a programming language. So if you want to specify your syntax of your language, you might give a formal grammar like Bacchus-Naur form, BNF grammars. And what we're going to do in this course is we're going to go past Bacchus-Naur form, which tells us what the syntax of the language looks like where the semicolons and the curly braces go, to specify what a programming language actually does. And so we're going to show how you can give mathematical definitions of the semantics or behavior of a program. And so the benefit of having this semantics is a way of, it's a way of specifying a contract between a programmer and a language compiler implementer. So if a program has a weird behavior, you can go and ask the compiler writer, was this a bug? And then they can both jointly look at the specification to figure out whether the programmer misunderstood the language or the compiler writer has misimplemented the programming language. And in this way, you can sort of come to an agreement about who needs to change. But there's more benefits of this beyond just sort of this legalistic aspect. It's also a useful tool for language design. So if you've written down your language design, you can see the choices that you've made. A programming language, any programming language, is much bigger than someone can keep in their head at all times. And if you're thinking about the interaction of the features of a programming language, well, now you have something more than you can keep in your head, and now you square it to get all of the possible interactions. And so if you actually just write things down, then having them written down means you can look at them and think about whether the design makes sense at all. And so it's the usual thing of you can write things down and that'll clarify your thinking. And if you get a design that's clean enough, now you're in a position, and precise enough, a mathematical definition, now you're in a position to start thinking about proving properties of the whole language, such as type safety or decidability of type inference, or memory safety, or any of these other things. And the thing is that once you have one of these properties of the whole language, there's a property that every program in the programming language that you could possibly write satisfies. And this makes reasoning about your programs, designing your programs, much easier. So it's much easier to build an abstraction if you know that there's no way that a client of your program can't subvert the abstraction. And then once you start relying on these whole language properties, we start thinking, okay, and now we want to prove properties about specific programs. Perhaps you might want to prove that your banking software isn't leaking your financial data or something like this. And so this would be a property of a specific program, and to even articulate or state a claim like that, you need to know very well what that program actually does. So all of these things rely on having a semantics. And the more precise the semantics is, the easier these questions are to answer. And so when you sit down to design a programming language, one thing you'll notice straight away is that there are a huge number of design choices, starting from the very smallest things all the way up to high-level things. So, a basic question might be, what is a value? And, a language like C says, well, my basic values are typically small objects, so things like bytes or words, or sometimes sequences of bytes in memory that represent things like structs. Whereas a language like Java has a much richer notion of its basic value. It says I have basic values like integers and characters, but I have this other class of basic values which are objects. And objects are an extremely powerful basic value that's powerful enough to encompass both data and code. And language like, say, ML will say, okay, well, you have the ability to not just have the primitive data that's built in, but you can also declare new data types that create new forms of data that the program can talk about. Of course, Java can do the same thing with a new class declaration as well. But the question of what the values are is like a fundamental choice, and it has a lot of implications already, like how you can compile the language, what the memory management strategy is, how it affects concurrency, all the concurrent behavior of the language, all these things affect even the question of what the basic values of a programming language are. And then you have questions like evaluation order, like does evaluation order happen from left to right or right to left or in an unspecified order? And all of these have issues, like have consequences, because the order in which you evaluate terms affects the runtime of your program. And it also, how tightly you nail down the evaluation order also affects affects the freedom that the compiler has to optimize your program. Because if you tell it, any evaluation order is fine, then it'll be able to choose a good one at the expense of making the actual behavior of the program harder to understand. And I talked a little bit about how in C the basic values are much less sophisticated than in a language like Java. And the second question is, what can be stored where? So what kinds of values can you store in variables? What kinds of things go on the stack? What things live in the heap? Does the programmer have control over all this? All these things affect the whole compilation story of the programming language. And all these choices about how your runtime behavior of your program and how your runtime representations work also affect what kinds of compile time and runtime guarantees that you can offer. And if you start thinking about these things, okay, what kinds of guarantees I can offer, you start thinking, okay, how do I keep control of effects? How do I support concurrency? Things like this. So, for instance, the Haskell programming language is famous for its support of monads, which are a type system feature for controlling when and where effects happen. And the Rust programming language is famous for having like a very strong ownership discipline on your Rust values, which enables like a great deal of support for concurrent programming, because it lets you statically rule out many kinds of concurrency errors like race conditions. And languages like OCaml have module systems, which are very powerful and enable information hiding and large-scale development in powerful ways that other languages haven't. And again, like all of these choices influence each other. So the choice of what your basic values are affects how concurrency is supported, and concurrency affects whether and how information hiding works, because a concurrent computation can sometimes see intermediate states of your program. And so all of these things interact with each other, and you have a lot of degrees of freedom at each point. And how do we actually see how these things can affect? So, C is famous for being a low-level language that leaves a lot to the compiler. And so in a normal term, we would have a show of hands about how people think about these examples of how programs work. And so what I want you to do now is, when you're listening to the lecture, like, I'm going to ask you a question. If x is initially 3, what's the value of the following, where we do the post increment x++, and we add it to itself 4 times. And so you can think, okay, well, is it 3? Is it 12? Is it 13? Is it 14? Is it 15? Is it 16? Is it 17? What's the value that this computes? And so I want you to just think about the definition of this post increment, which means return the value and then increment the variable. And I want you to think about what it could return. And so I'll just wait for a second. Okay, if you've thought about it, then the answer is it's actually a trick question. This does not have a specified behavior according to the C standard. In fact, this is a case of undefined behavior. And the reason is that the C standard says that the addition operation does not sequence side effects between the things on the left-hand side and the right-hand side. And the C standard says, okay, and if you have 2 operations that have a side effect, if they don't have a sequence, if they are unsequenced, then the result is undefined. So you have undefined behavior. And so x++ is an operation that has a side effect. It's going to increment the variable x. And so we have x++ plus x++, and the answer is it's undefined. C can return 3, it can return 4, it can return 12, it can return 192 million, it can corrupt memory and hand over and exfiltrate your entire hard disk to Bitcoin miners. Anything is allowed according to the C standard. So this is undefined behavior. Okay, so that's a little bit of a surprise. Okay, well, let's look at another language here. And so C# is Microsoft's version of Java. And one of the things that distinguished C# for a long time from Java was that C# had support for first-class functions, and while Java did not. So Java got support for lambda expressions in Java 9, and C# had it considerably earlier than that. And the way that C# writes a function expression is it's called delegate. And so if you've written JavaScript, this is sort of like the function keyword. And it says, I'm going to create an array of functions, which is going to have 11 elements in it. And then I'm going to iterate from I equals 0 to 10. And at each step in the ith element of the array, I am going to store a function that returns I. And so you might think, okay, well, I is going to run from 0 to 10, and then I'm going to store a function in this for each of those 11 elements. And then once that's done, I'm just going to iterate over that array, and I am going to call that function. Okay, so the question, of course, is what does this function actually do? And so if you just look at the code, you might think, all right, when I is 0, I'm returning a function that returns 0. When I is 1, I'm returning a function that returns 1. Is that what happens? The answer is no. It returns 11 for every single one of those functions. And the reason is that the for loop in C# does not bind a new variable in each iteration of this loop. You have one iteration variable, and it gets incremented on each iteration. And so every one of these functions is referring to I, and I has gotten incremented from 0 all the way to 11. So every single one of those functions returns 11. for a long time, JavaScript worked in a very similar fashion, and this was a big enough problem that they actually changed how Java. They added a new kind of for loop in Java to make make things work closer to the way that people expect it. And speaking of JavaScript, here's a function in JavaScript. So we have a function bar which takes an argument x, and then we have a bar immediately returns an anonymous function. And what this anonymous function does is it initializes a variable x with the x that bar received and then returns it. So if we write var f equals bar of 200 and then we call f, what should come out? And you should be thinking, well, I would expect it to return 200, but I'm getting this in a lecture on semantics, so it's probably a trick question. And so let's try that. And so now what we're going to do is we're going to say var x is equal to x. And now we'll return x. And now we have our function bar. So bar is a function, and what we'll do is we'll say var f is equal to bar of 200. Okay, so f is a function, and so let's call f. Oh, look at that, it's undefined. Why could that be? And the reason for this is that the way this var declaration works is secretly it's declaring a variable, initializing it to the null value or the undefined value, and then it's setting it equal to x. And now this x is referring to that x. And so it never even sees this x over here. So let's make one small change here. So let's make this into var y and return y. And now let's do var g is equal to bar of 200. Now let's call g. Aha! Now it returned 200, which worked the way we expected. And the reason is that this variable y does not hide the binding x. So the var declaration in JavaScript is a bit strange. It has a behavior that doesn't work quite the way that you might naively expect. And so if we want to say what the language actually does, we can't rely on our pre-theoretical or like informal expectations. We have to actually say what the language does if we want to explain its behavior. And so or you know, in a better world, to improve its behavior in future versions. And so when we write down semantics for programming languages, there are three major styles of semantics. There's operational semantics, there's denotational semantics, and then there's axiomatic or logical semantics. And the idea behind these three methodologies is that they each have a different approach. And so the idea behind an operational semantics is that it's a semantics that describes the operations of a program. So it tells you how the program evaluates. So you give a sort of abstract machine, and you use that abstract machine to say how one program will take steps and possibly eventually reach a value or final answer. And so this is a good way of describing precisely what programming languages does. It's a bit fiddly and massy. Like these definitions can be quite large, but they can be quite large in the service of faithfully representing what the programming languages that we actually see in the wild actually do. And so in this course, we're going to focus mostly on operational semantics because we want to get across the idea that we actually can say specifically what a program does. Second, there's a style of semantics called denotational semantics. And here the idea is that you can take a programming language and then interpret each program as a kind of mathematical object. So you might say, okay, I'm going to interpret every type in my programming language as a set of possible values, and a program is an expression which takes on a value within the set for that type. And so now what you gain from a denotational semantics is the ability to use all of mathematics when you're defining what your programming language does. So what you can do is you can if you define your semantics in terms of classical mathematical structures, then you have all of the theorems that mathematicians have proved over the last 2,000 years to help understand what your program means. And so denotational and operational semantics are often sort of put in opposition to each other, where denotational semantics is taken to be a sort of more mathematical approach, and operational semantics is sort of taken to be a more engineering approach. But fundamentally, like these two styles of semantics live in a sort of dialectic with one another. So you can say that a program represents a mathematical object, but you need to prove somehow that it computes something that's compatible with it, with your mathematical expectations. And so operational and denotational semantics tend to go together. And then when you start thinking about what an individual program actually does, this is where axiomatic or logical semantics comes into play. And the idea here is that you give a sort of axiomatic characterization of what each construct in your programming language does, and then proving that a program does something is a matter of proving lemmas about your program structure using all these axioms that you know about the behavior of each component. And next year in the Hoare logic and model checking course, you'll be able to see how this works. And it turns out that if you have a set of axioms describing a programming language, you want to know that they're correct set of axioms. And in this case, you often turn to validate your axioms against an operational or a denotational semantics. So sometimes you'll see these three styles of semantics contrasted against one another, but they all end up sort of like supporting one another and depending on one another. And in this course, we're going to focus mostly on operational semantics. And so another thing that comes up is that a real programming language is very, very large. So language specifications can run to hundreds of pages long, and if you hold the specification to 300 pages or less, people will call your language very minimalistic. And often what happens is that a programming language will have many different ways of expressing the same thing, because languages are artifacts that are built by teams of people over the course of decades, and as people have better ideas, they add things to the programming language, and it can be very hard to take anything out because there's sometimes millions or even hundreds of millions of code out in the wild, and it would just be too much to come and break existing code. And so there will often be redundant constructions in the programming language, and these redundancies are sometimes exact extensions, and sometimes they're just partial overlaps stemming from the evolutionary design of the language. And so these large, complicated languages are often a lot of work to specify anything about. And so when you're trying to understand how a language works, one thing that's extremely useful is to use a model organism. So biologists, when they want to study genetics, the first thing they turn to is not humans or even animals like rats. They look at fruit flies, because the fruit fly is a much simpler organism, and it can be, you get it in much larger numbers, so it's easy it's easier to study many questions about genetics and evolution when you have a model organism. And in the same way, when you're trying to understand programming languages and how programming languages features interact, it's a good idea to have a model organism, which is going to be some kind of small or toy language that supports just the features that we're interested in and with no others. And then when we understand like how that collection of features interacts and how it works together, then we can scale it up to a larger scale language. And it turns out that even very small languages can involve very delicate design decisions because whenever you have multiple features, you have a lot of possible interactions that you need to consider. And so what we're going to do in this course is we are going to look at the operational semantics and typing for a very small little language. It'll start out with the language, we'll call it L1 for language 1, and then as we add things to it, like the number will get bigger. So we'll have L2 and L3 as well. And so what we're going to do is we're going to look at this language, and we're going to look at two of the essential ways of specifying what a programming language does. We're going to show how you can take a little tiny language and give it an operational semantics to show how a program evaluates when it's executed. And secondly, we're going to show how to specify the type system for a small language. So we can write down any kind of BNF grammar that we like, but a BNF grammar can't ensure that a variable is in scope or that it's type correct or anything like this. And so what we'll show you is how to specify a type system for a language and how to specify its operational semantics. And then what we will do in the context of this little language is we're going to develop the tools that will take you from saying, okay, I have a type system for a little programming language and I think it makes sense. We're going to take you from there to actually proving something about the programming language, to knowing that it actually is type safe. And to do so, what we're going to have to do is we're going to have to introduce a number of additional technical tools. Like we'll learn about abstract syntax, what it is formally. We'll learn about inductive definitions, which is how we specify operational semantics and static semantics like typing. And then we'll show you how, once you have these semantics, how to prove that the language has the property that you wish it did. And then after seeing how this works in the context of a very tiny language, what we'll do is we'll steadily add features to the language so that we can support features like first-class functions and data types and references and pointers and things like this. And then once we understand how this recipe for type safety proof goes, we'll look at more exotic language features like subtyping in objects, how we prove that two programs might actually be semantically equivalent. Recall that one of the most important applications of semantics is actually justifying the optimizations that compilers do. And then what we'll do is we'll see how all the stuff we learn, which will primarily be focused on sequential languages, we'll see how it starts to look when we add features like concurrency to the programming language. And so we'll have a bit of a here you can see the dependency graph here. What we're going to do in the first several lectures is look at this L1 language, which is basically a while loop language. So you have locations or registers that can store values, and then you have sequential composition, if then else, and looping. And then we will extend L1 to additional features like functions and recursive definitions. And then after having done that extension, we're going to look at further extensions like more data types like records and sums and pointers. And then we'll see how we can even push it further to advanced features like objects and subtyping. And similarly, we're going to look at semantic equivalence to see what kinds of program transformations preserve the meaning of a program, and we'll also see how all of these issues are affected by the introduction of concurrency. Okay, so the sort of the big picture of the course is that semantics is sort of a bottleneck for a lot of the stuff in the tripos. So we're going to bring together all kinds of courses you've done, like discrete maths and logic and proof and ML programming, and we're going to use this as ingredients in the tools and techniques and methods that we use in semantics. And then once you've done semantics, there will be many courses in part 2 that sort of rely on this. So like types and denotational semantics and topics and concurrency, all of these things will rely on the ideas introduced in this course. Okay, and finally, before I wrap up this first lecture, let me know if you spot any typos in the slides and if I'm going too fast or too slow. These kinds of online lectures are a bit new to me, and any kind of feedback that you have will be very important for me to adjust my approach. So there are exercises in the lecture notes, and you'll find implementations of the languages that we look at on the course website. And finally, the recommended books. If you can look at them, they'll be really useful. And all of these books have a common property in that in the first chapter they set up a lot of their basic framework, and when you read it, you don't understand it. And my advice is, once you read chapter 1 and you don't understand it, go on to chapter 2. Just don't worry about that lack of understanding, because what's going on is you need to have some specific examples in your mind, and then once you have those concrete examples, you come back to the first chapter, and then it'll all make sense. Okay, and soon I'll start it with the second lecture, when we'll get into the actual semantics of our initial language, our first language, L1. Thank you very much.